My name's Anna and I'm applying to NYU Current's Atmosphere and Ocean Science program. Ever since I was a little kid, I loved mathematics, even if I didn't really know what it was all about. So I decided to go to University of Chicago for my undergraduate studies and study math. While I was there, I realized that even though areas of mathematics like Galois theory and number theory and group theory are powerful and elegant, they weren't really what I was interested in. What I really liked was my geophysics classes, where I could study these tangible physical phenomena that explain the everyday world I saw around me. At the end of my undergraduate career, I decided that I needed to learn a little bit more about applied math because I hadn't had the opportunity to see it as an undergraduate at Chicago. So I decided to go and pursue a master's degree at King Abdullah University of Science Technology, or KAUST, which is a startup university in Saudi Arabia that's currently in its 4th year. While at KAUST, I've had the opportunity to study a lot of numerical topics that I hadn't seen before and have really enjoyed learning about, like numerical linear algebra, computational fluid dynamics, and PDEs. But what I really enjoyed the most is the research I do in geophysics, and so that's why I picked the central limit theorem to talk about today. Because in applied science, we really need to be able to model things, and the central limit theorem is a powerful theorem that allows us to approximate phenomena that we may not be able to describe mathematically by a normal distribution, which is something we all know and love well. So, for example, if we had something like Saudi rainfall, which is most of the time is non-existent, but every couple of days a year there's a couple millimeters of rainfall, and then maybe once every other year there's a huge deluge and it floods, and there's about 2 meters of precipitation. If we wanted to sample something like this, the central limit theorem would allow us to approximate an average distribution. So mathematically what this looks like is that we have Sn, where Sn is the average of n variables, where xi are all independently identically distributed. So, and we know their mean and their variance. So if they have a mean of mu and they have a variance of sigma squared, where for convergence we need that sigma is greater than 0. And what the central limit theorem tells us is that if we rescale Sn, which is the average of all the sampled random variables that we pull from our original unknown distribution, then we get a distribution function that looks a lot like normal. And in fact, the convergence is pointwise. So we can say that square root of n times Sn minus mu, this is our scaled Sn, is simply distributed normally with a mean of mu and a standard variance of sigma over square root of n. And this looks a lot like the original variance in mean from our original distribution. Something like this is particularly powerful and in geophysics, and one area that we use it a lot in, one area that I use it in, is my own research in statistical significance tests for atmospheric trends. So in geophysics, a lot of the things we look at have to do with anomalies, like temperature anomalies, for example, where we have, some data that honestly often just looks like Gaussian noise. But what we need to do is we decompose this noise somehow into like a noise and a signal, and this will give us this is the trend that we have. So if we can approximate some sort of anomaly by some trend, and then we can take out the noise. We can compute, what I do in my research is we compute whether or not this trend is statistically significant by examining the distribution of the errors. And one approximation we can make using something like the central limit theorem is that these are normally distributed. So I'd really like to continue doing research like this in my future work, and I'm applying to NYU so I can really become a researcher and maybe one day a professor. I enjoy doing research like this, and I want to work with people who are more mathematically inclined. NYU's Atmosphere Ocean Science program is really the perfect program out there because it's the most sort of mathematically inclined out of all the ocean and atmospheric and geophysical programs.